Here we have a glycerol molecule, and there are 3 carbon atoms bonded to each other, the 2 hydrogens on the end, and there is 1 hydrogen on the center one. Then there are 3 hydroxyl groups on the ends also. There are 2 oxygens on each, and then there's a terminal hydrogen on each one. So glycerol is important because it is the backbone for bonding together 3 fatty acid monomers into a fat or a triglyceride polymer. So I'll put that aside. And here we have a long fatty acid chain. It is mostly a hydrocarbon until you get to the end where there's that double bonded oxygen on the end. And this one has 2, 3, 4, 5, 6, 7, 8, 9 carbon atoms. And each carbon atom is bonded with a single bond and then a double bond to an oxygen at the very end. And there are hydrogens all along. This is a saturated fatty acid. So then we have just 3 copies of the same molecule. And we want to bond them together onto this glycerol backbone in order to make a fatty acid. So to understand how this reaction proceeds, let's do it with the model. So first we have to pop off the OH from each end of the glycerol. And we'll set those aside. And then we have to pop off 1 hydrogen from the end of each of the fatty acid chains. Then we bond the 2 oxygens, or I'm sorry, the single oxygen onto the carbon where the hydrogen had been. Now we have our gigantic molecule of a fatty acid, or I'm sorry, a triglyceride made of 3 of the same fatty acids. If this were a phospholipid, the bottom one would be a phosphate group instead of a fatty acid. But as you can see, there are a lot of bonds here, so that's a lot of room to store a lot of energy. And you can pack them tightly together. Since this is a highly saturated fat, all of these fatty acid chains will pack together nicely and take up less space. And the fact that you can pack them together densely, that increased density is why these highly saturated fatty acids, when you put them into a fat molecule, are solid at room temperature because they pack together so nicely. So if we put that aside, then we have our leftovers from the reaction, which are the OH groups and the hydrogen atoms. So if you put those together, you get water molecules. So we have 1, 2, 3 of them. So since we are removing water molecules as a net process from the rest of the molecule that we bonded together, we would call this a dehydration reaction. Now, when we digest lipids, we have to break down these bonds, and that requires water to be present in order to take the place of the missing bond sites on the ends of each of the molecules when we separate them back out. So that would be a hydration reaction when you break down a fat. dehydration when you build one.